Hello, this is Dara Semi, and in this course I would like to talk about the introduction to computational fluid dynamics, or in short, CFD. I'm a Master of Applied Science student in Gina Cody School of Concordia University, and the course begins. CFD is a course about how to deal with governing equations of fluid mechanics. And fluid mechanics are governed by many partial derivative equations. And if you probably know, dealing with this kind of PDEs is hard. And finding analytical solutions for these PDEs, for these equations, is very hard and nearly impossible. So to come up with a solution, we use computers and numerical methods to solve these PDEs. CFD contains mostly three methods: finite difference method, finite element method, and finite volume method. In CFD courses, mostly just finite FDMs and FVMs are covered. While FEMs are important methods to be used in fluid dynamics, they're not covered because they're mostly related to strength materials, statics, and mostly solid courses. And nowadays, FEMs are not used in fluid dynamics. So briefly, I need to just do a categorization for PDEs to just know how to deal, because algorithms for solving these methods are different by their category. First of all, PDEs are defined by their linearity. Some of them are nonlinear, some of them linear. You see an example of linear equations, which can be modified as known as simple heat transfer in one dimension equation. Also, there are many nonlinear equations as well. You can see the equation here. The difference between linear and nonlinear is that if you think that t and x are independent variables, u is dependent on t and x. If our differential equations contains terms of u powered or some functions of u, which is a dependent variable, that equation will be considered nonlinear. For example, in here, the linear equation, alpha is just a constant, a number. No variation, no dependence on u. In this nonlinear part, we see a term that contains u. For example, this is a f of u, and u here is u powered, u squared. This is the first categorization we need to make. Also, we will see this much in future when we are going deep through defining the algorithms to solve these equations. And we separate equations by three parameters. So let's see the equation 1. This is the general form of a PDE with a degree of 2 actually. We do not go to upper degrees like 3 or 4. Here, first of all, we should make sure this is a linear function. A, B, C, D, E, F, G, all of them are constant numbers, and there is no nonlinearity. And these constants do not dependent on the phi function, phi variable. And based on these constants, the function is defined in three names. If b squared minus 4 times a c and c is below 0 and be negative, we call it elliptic. For example, we have Laplacian famous equations. And if you plug the constants in the equation 1, you can see b is 0, a is 1, c is 1. So 0 minus 4 times 1 is less than 0. So we consider this equation elliptic. This can be done in three other categories as well. If b powered 2 minus 4 times a and c equals to 0, we call it parabolic. For example, most of transport phenomenons, just conduction. For example, we have a non-unsteady one-dimensional conduction heat transfer here. If we plug it in equation 1, we will see that 0 minus 4 times alpha times 0, we can replace y with t. The 0 minus 4 times alpha times 0 is 0. So we will call this equation parabolic. For more information, there's a very good blog in this topic, and you can check it out. I provided the link here. Okay. After this brief introduction to how we categorize PDEs, now we need to see how we do discretize these PDEs. To discretize these PDEs, we need to know some basics. Probably you had Taylor Swift in your high schools, but we will go through and relearn the concept again. The Taylor series is a way that is described in equation 2 and 3. Equation 2 is the extended form, and equation 3 is the compact form. N is the degree of the Taylor series. For each degree, if we want to expand this, we will reach a form of equation like this. For example, this is the extended form of the degree of 3, because the last digit we see in the discretization form is 3. For getting more understanding of Taylor series, let's do this kind of write this Taylor series for a famous function of sine x. If we have a sine x and we go to the degree of 3, actually, if you see, we need some derivatives. The first derivative of sine is cosine. The second derivative of sine is minus sine. Or is this first derivative actually of the cosine is the minus sine. And the third derivative is minus cosine, or just simply the first derivative of this function. If we have these derivatives and write this form, sine in the first x0 is the target value of ours. If you, for example, consider this as 0, fx will be considered as x if of in the near of 0, f at the x when the x is equal to 0, times by x by the first derivative plus x powered by 2 divided by 2 in the second derivative, and so forth. You see that how it works in the near of x 0 if you consider it as a 0. Actually, Taylor series are somehow approximation to functions that are not polynomial, because dealing with polynomials are much easier. If you plot them, you see something here. Um, the blue line is the exact function, and the other colors are the degree of approximations we would like to have. For example, x, just x, which is a line, is the first approximation of Taylor series for sine. As you see, it aligns perfectly in these regions with the blue line. But if we move forward or backward, we will see they diverge quietly, and there is a problem. So if you go to more advanced, more expanded series, for example, this is number 3, Taylor series with approximation of degree 3, the green one. You can see the blue line and the green line aligns in a bigger range. And if we go to degree of 5, you can see this range expands better. There's an illustration in YouTube by Rakesh Kumar, made with Manim, and it illustrates the Taylor series very good. As seen, the exact function is cosine of x. The first degree, or 0 degree, which is just a flat line, is 1, and do not perform very well just in one point. If I increase the degree, for example, going to degree 2, you can see in the wider range, it approximates the value of the exact function. And as we go to, for example, degree of 8, you can see it is much better. So there are some references and some illustrations that are all provided in these links. I suggest you to go and look them. They are very good and very help you to find about Taylor series. Thank you, that's all. I think I reached the 10 minutes, so thank you very much.